Our speaker for today is Professor Michael Tam. Professor Tam obtained his bachelor's and PhD degrees in chemical engineering from Monash University, Australia in 1982 and 1991 respectively. He taught at Nanyang Technological University, Singapore for 15 years and joined the Department of Chemical Engineering, University of Waterloo in 2007 as a tenured full professor and holds the position of University Research Chair in the field of functional colloids and sustainable nanomaterials. His research interests are in colloids, self-assembly systems, polymer surfactant interactions, and drug delivery systems. He has published more than 400 journal articles in various fields of polymer science and engineering. His total citation exceeds 28,000 and his H index is 89. He is also a deputy editor of ACS Sustainable Resource Management. So thank you, Professor Tam, for joining us. The stage is all yours now. Thank you so much.
Thank you, Neha. Welcome to all the participants. I'm very happy to be able to share some of the work that we are working on and also to talk about the journal that I'm involved in. Can you see my slides, Neha?
Yes, Professor Tam, please go
great.
ahead.
So the topic of my talk today is innovation in sustainable nanomaterials for advanced engineering application. Welcome to this series, and I'm very pleased to be able to share with you some of the innovation that we have been working on for the last couple of years. So for those who are not familiar where Waterloo is, it is situated near Toronto in the horseshoe hub between Detroit and Toronto. If you know of BlackBerry, that's where it was founded. So BlackBerry was invented at the University of Waterloo, and there are many high-tech companies established because of the nature of the university. So one of the issues that we need to really address now is the CO2 issue of climate change. So you look at this cycle, you have the sun, and we as chemical engineer or chemists has developed a lot of reaction or system that resulted in the emission of carbon dioxide. And unfortunately, over a number of years, there is a increase in the accumulation of CO2 due to the release of CO2 from many processes. So if you look at this cycle, there's one living species that is able to at least partly deal with the CO2 issue, and that's the plants. Right? Plants extract CO2 combined with water through a process called photosynthesis using the free energy from the sun. And if we can extract materials or resources from plants, then we can contribute to mitigating the CO2 issue if you do not combust the cellulose. So in this talk, I'm going to discuss how we could utilize materials from nature and try to use them to develop technology to remediate some of the challenges that we are facing. So here's a technology that was developed in Canada, where Canada has lots of trees. If you deconstruct the wood chip to a certain level and stop before it becomes cellulose chain, then you get these nanoparticles. They are crystalline. We call them nanocellulose or nanorice. So these systems are very stable. They are very well dispersed in water. They're non-toxic. They're renewable. And now there's a plant in Canada that produces 1,000 kilograms per day. And you can do a lot of chemistry on the surface of the material. So here is the plant that was built in 2012. Behind is a pulp mill. And in front is the plant that processes the pulp here, and then clean the particle, and then dry the particle. It's a very simple, continuous process. And the person that's involved in scaling the plant is Dr. Barry. He brings the technology from the bench scale to the production scale. And the plant now is operating and producing 1,000 kilograms of CNC per day. So we have been working on this since 2012, where we received this dry powder. Typically for nanoparticle, if they are dry, it's very hard to redisperse them because of the attractive force. But for this particular particle, because of the chemistry, I put them in water and they get very good dispersion. So which is very, very important if you want to process them for different application. Then if you want to formulate into a product, you add surfactant or you add different types of material. Sometimes you get this phase separation or aggregation. Is it good or bad? That depends on your application. Even to remove arsenic from water, then this is desirable. So that's good. If you want to make, let's say, cosmetic or emulsion or food products, then this is undesirable. Then you can do some chemistry by functionalize the surface, and you can go back and forth to be able to engineer different types of functional material for application. So we have used them to stabilize emulsion. We have produced quantum dot on a CNC that are very stable, and we shine UV light, it fluoresces, so that's a good for imaging. And we can coat this particle with conductive polymers to make conductive ink for different electronic application, and we can nucleate various metallic or inorganic nanoparticle on the surface and produce systems that have antimicrobial properties. So in our research, we take pristine CNC produced from the plant, and then we engineer them by putting organic molecules on the surface, metallic particle or inorganic system, and make different types of material. And then we can, in Waterloo, we want to incubate startup to try to engineer the material for various applications. And these are our collaborators for the last couple of years. So I'm playing you a video that describe the research in my group. And this video was produced by one of my co-op students, and he has a very, very interesting interest in media. So I'm going to play this with you that summarizes the research in my group.
Human civilization and industrialization inevitably occur at the expense of Mother Nature. A promising strategy to reduce the carbon footprint utilizes trees which have a mass carbon storage capacity. Our strategy is to harness harmful emissions such as carbon dioxide and convert them into nature-inspired sustainable materials. The intricate design of the plant cell involves uptake of CO2 to generate energy for trees through the process of photosynthesis. The process begins at the molecular level when carbon dioxide reacts with water using energy provided by the sun. This produces glucose, which is used as an energy source and for basic cellular maintenance throughout the cell. Glucose is stored in the cell wall in the form of cellulose fibers, which provide strength and energy reserves. This basic subunit of life can be exploited for creating a sustainable future in nanotechnology. The scale-up process begins when highly organized cellulose fibers derived from wood undergo acid hydrolysis to yield the crystalline domains of the fiber, known as cellulose or nanocrystals. The crystalline rods have remarkable surface area and mechanical strength, providing a unique avenue for the prospect of scalable and sustainable applications. Some of these applications include grafting of polymer brushes for wastewater treatment, cosmetic and personal care, preparing emulsions, and oil and gas. Surface modifications with functionalized coatings and metal oxide deposition can be used in food, healthcare, and agricultural applications. The Laboratory for Functional Colloids and Sustainable Nanomaterials, led by Professor Michael Tam, seeks to develop novel nanomaterials for various applications, such as in agriculture, cosmetics, personal and home care, and oil and gas. We collaborate with companies like Celluforce, 3M, Ecosynthetics, Medela Health, and many others. Our goal is to develop innovative solutions by harnessing sustainable nanomaterials, such as cellulose nanocrystals, and transform them into useful products. Our vision is to make Waterloo an innovative hub for startups in sustainable chemistry and engineering that will create jobs for Canadians.
So in my group, we basically take these two types of nanomaterial. One is nanocrystal, the other is nanofiber, and we exploit them for biomedical, for environment and water, for food and agriculture, or consumer and personal home care. So those are different types of applications that we can exploit this material. I'm going to illustrate some of this with some examples. So when we started this work, our founder, the Celluforce, was very interested in filing various types of innovation. So through them and to the university, we have now 5 patents that's been approved, and we're trying now to commercialize some of this technology. So the first is the functional CNC as antimicrobial compound. So what we want to do is to take this CNC as a carrier for active antimicrobial compound, in this case, waste from the plasma spray system. Copper nickel zinc is a powder that's produced as a waste. And we know that copper and nickel has very good antimicrobial application. So we take our nanoparticle, we then coat it with dopamine to provide adhesion. And then we then adhere this nanoparticle on the surface of this nanoparticle. As you can see, we can coat them and they are very stable. So we have a very simple assay to try to evaluate their performance. So what we do is that we culture yeast, baker's yeast, with sugar, and then we add different amount of nanoparticle to this yeast system, and then measure the amount of CO2 release as an indicator of the impact of the material on the antifungal property. So here's the illustration. On the left is a control with 0% of this compound, and then on the left to right, you have 45, 90, and 180. So we measure the CO2 release from the inverted U tube, and then from the volume of this CO2, we can then plot this relationship. As you can see, as you go from left to right, at 180 ppm, very little CO2 is being released. And from this data, we can chart this volume of CO2 release versus time. The black circle is the control without any nanoparticle. As you increase the concentration, as you can see at about 100 or so ppm, you have two results. Very large reduction in the CO2 release, and also the slope also reduced. So the rate of CO2 release and the amount of CO2 release is a function of concentration of this nanoparticle. And then we can plot this CO2 release versus the concentration, and from there you can determine for this particular system, about 100 ppm would be sufficient to prevent the yeast from producing CO2. That could mean that the yeast had died, or the yeast metabolic activity is being substantially reduced. The other system that we have worked on, which can be used as an antimicrobial compound and a catalyst to convert this amino compound, is to coat this nanoparticle with silver. So we basically take this nanoparticle and then we coat it with the dopamine and use the silver ion to silver nanoparticle, which are quite small, between the 2 to 5 nanometer. As you can see, in A is our dispersion. You can see very good dispersion over a long time. B is the silver nanoparticle prepared without this coating. As you can see at the bottom, you have agglomerate of this silver in this solution. Then we do a bacterial test. So this is the gram negative. With the CNC, as you can see, on the with silver nanoparticle, we have very good performance, 4 times better. We need 4 times less of the material to reduce this bacterial in the plate count. For the same result for gram positive. So with this CNC system, we can reduce the amount by 4 times. It's more effective because higher surface area. And as you can see, when we published the paper, they wanted some evidence of how it works. So we have this TEM. As you can see here, this is the CNC with silver. They are being transported like a nano submarine to the surface of this bacteria, releases the silver at the site, and that really reduces, and it's more effective in reducing the activity of the bacteria, kill the bacteria. So the next topic I want to talk about is the using CNC as a conductive ink. So I have a very good PhD student who finished many years ago. So he came to me and she wanted to work on energy because that was a very hot area. So I mentioned to her, I said, you can work on energy, but you must use CNC. So she had a good idea. So she came up with an idea of taking a conductive polymers, which has very good conductivity and capacitance. However, polypyrrole or pyro it's very difficult to process. It agglomerates, it's insoluble, it has poor mechanical properties. Hence, as you know, conductive polymers was awarded a Nobel Prize, but the utility has been really not as widespread as many other material. Then we have CNC. It has very good mechanical properties, good dispersion, high surface insulator. So we want to remove those negative properties indicated by red and only maintain the good properties indicated by black. So we marry the two. The question is, can you preserve the beneficial properties and make this hybrid to be useful as a conductive ink? So let's see what she proposed to do. So she took this CNC, oxidized it, and put carboxylic acid groups on the surface. The reason was because you can then induce hydrogen bond between the monomer, the pyromonomer, and the surface of CNC, resulting, as you add the APS persulfate, then you can oxidize and polymerize this. From the bottom, you can see as the solution becomes black, is an indication that the reaction is proceeding. And then you basically polymerize the coating of the conductive polymers on the surface of the CNC. So what was done is that we look at the ratio of the pyromonomer to the amount of OH groups on the CNC. As you can see, we measure the conductivity. Our result shows that with the ratio of 16, you get the optimum conductivity. Insufficient, lower amount result in insufficient coating, you get poorer conductivity. Too much, resulting in multi-layer, you result in delamination. So the optimum we found was 16. So we were able to convert an insulator, which is a wood fiber, into a conductor that's near the region where it can conduct electron. So additionally, this material is able to store charge. As you can see here, the specific capacitance of various types of well-known material like carbon nanotubes, graphene, has very good capacitance, but our material has comparable, if not better, specific capacitance, suggesting that this particular material is also able to be used as a storage for energy, as a capacitance. So, however, during the cycling tests, after 1,000 cycles, there was a reduction in the capacitance by 30%. So the issue is, what's the problem? And we found that the problem is due to interface. So we solved the interfacial problem because when you do cycling tests, the interface delaminate and hence you have poor properties. So we add polyvinyl pyridone to try to provide an interface that provide good adhesion between the conductive polymers and the CNC. And this reaction is easily done, and we optimize it and found that about 10% coating would give you a very, very good interface to enable the conductive polymers to be polymerized on the surface. So I can see here, on the left is the generation 1. As you can see, the nanoparticle, the coating is not very smooth, right? There's irregularity, and that's evidenced by the TM picture. And that results in a 30% drop in the specific capacitance under 1,000 cycles. Then on the right is this new coated system. You see that you get very uniform coating, and that results in the capacitance drop of 5%, high capacitance and a drop of 5%. So interface is very, very critical in regards to making material that's stable for, in this case, charge storage.
Hi everyone, this video is going to demonstrate that our conductive CNC is able to light the bulb. You see this black powder is our synthesized conductive CNC. Then we press it into this black sheet, and now we're ready to go. The picture is a robot, and the heart of the robot is this LED light. One end of the LED is connected with this battery, and our black sheet is connected to the other end of the LED. Now, let's make the robot heartbeat.
So now we have a system that is able to conduct electron, and 3M is very interested to print this onto some of their electronic system. So you can do additional thing to this material by doping this particle of fiber with various systems. So you can see here, so these are our system. We can nucleate gold or platinum or palladium, and we see that the nanoparticle that we're able to put on the surface are very, very small. They are between less than 5 nanometer, which means that we can substantially increase the surface area and the processability of this nanoparticle to make sensors, to make catalysts and different types of application. So let me summarize what we have achieved. So this is the great thing about the forest, right? You look around left, right, and center in your house, there are trees. There are plants you can grow and grow all the time. So we can extract this nanoparticle, and that's being done now in Canada to produce this. And then we can coat it with conductive polymers to store charge, to conduct electrons. And then we can improve it by doing a interface coating. And then you can carbonize it, right? You can carbonize with oxygen, and that produces nanocarbon, and that can be used for some types of application. At the same time, you can then add nucleate or reduced nanoparticle onto this material to make different types of functional, sustainable nanomaterial that has different types of application. So let me just move on to the next topic, which is to regards to water. As you know, water is a very important commodity that society needs because of many activities and also climate change. Water resources is being depleted and the clean water is now not so accessible. As you can see from this chart, right, rain produces, give us good water, but unfortunately there are many activities. The rivers are contaminated now, and the groundwater, due to agriculture activities, a lot of pesticides are being leached to the groundwater. Hence, our water now is being compromised. We need to figure out a way to restore some of these water sources and to make water accessible and clean for society. So surface water is the most abundant water sources that we use. Lakes, rivers, streams, aquifers, those are water now that are being compromised due to many different types of activity on the surface. So what we want to do is to find new ways to remove those contaminants that's found in water. So in one of our patents that's been approved 2019, we have a very simple concept. We take this nanoparticle, and then we want to be able to build a structure that we can scale into a process. So we take cellulose nanomaterial that we can modify the surface, and then we mix it with alginate, as you know, this is seaweed, and then we extrude it into a calcium solution, and we get physical cross-linking. And now these nanoparticles are trapped within a porous structure. And now this porous structure beads, we can be from 1 millimeter to 10 millimeter, can now be put into a column, and then we can do remediation of this water in a very straightforward way. So as you can see, here is pure alginate, it's not robust. When you put CNC, you get very better properties, and the white nature is because the CNC now is impregnated into this alginate system, right? So our goal is to put this into a solution with contaminant, in this case, methylene blue dye, and to extract those dyes from the bulk water into the beads. As you can see on the right, if you have pure alginate, the removal of the methylene blue is not as good compared to when you have this high surface area CNC that's impregnated into the alginate bead. And this result shows that we have very good performance. So we want to compare the gold standard, which is activated carbon. This is the most common method used to remove contaminants in water. They are very effective and they're very good, but they're produced by high temperature process of these many types of charcoal material, and that results in a lot of energy and CO2 release. In many countries where they do not have access to this material because of cost, they then use their waste from the agriculture like rice husk, banana peel, orange peel, but the performance is not as good, right? Cheap, but not as good. Very good, but it's CO2 release and also costly. So our material is green, now has performance comparable to activated carbon, and these are produced in water with a low temperature process. And our result shows that it can be another source of adsorbent for some of the contaminants that's found in water. Then you can do chemistry to the system. So very simply, we coat it with dopamine, and then so now we have a dopamine that has specific affinity to, that's the methylene blue. So we then take this demonstration, we mix meta orange and methylene blue. As you know, this is physical mixing and gives you a different color green. So if you can remove, you find a material or absorbent, you can remove blue dyes, then you can restore this solution to have the yellow, orange, or orange solution. So we add our material to this, and you can see when you add our beads to this green dye, we remove methylene blue, and we now recover a solution that has only meta orange. So you can imagine sequentially introduce this material, different type of material. They are designed to remove specific dyes, and we can restore this system. So now we want to scale. We want to develop a process that we can then build into a system. So here is the continuous process. We have untreated water. We want to then put this beads into a column and just pump the thing through, and then we have cleaner water on the house. Okay. So my PhD student, Nate, built this system. So we want to be able to have a demonstration of a pilot concept where we know to make the bead in situ, right? So how you do that? We build a system where now we have this alginate and our CNC extruded into a dilute solution of calcium chloride, right? So this has 35 nozzles that we extrude, and then the beads are formed, and then they'll be transported to the column. And when the column is being filled, then we stop the production and we do the processing of these water, and that can be done continuously by control of the valves. So here is the example. So this is the generation of the beads. We extrude our alginate CNC into calcium chloride solution, and then we transport these beads down to the column. And now we wait, we continue to fill the column, and once the column is filled, we stop the production, and then we do the treatment of these water using the controlling the valve. And then now we can scale the technology. But before that, I had a funding from Grand Challenges Canada, which is like the Bill Gates Foundation. And the requirement of this funding is that we should take the technology to demonstrate in the third world country. So we link up with a university in Indonesia, in Yogyakarta, and we arranged to go to a batik factory, a textile mill. So I took my student to Indonesia, and we worked with some local student in the university, and Nate built this, and this is the column where we then set it up near the batik mill, and then we pump their dyes through our column. As you can see, this column is very dark blue, and eventually all the dyes are removed by our column. And at the end of the experiments, what we found is that we can now retrieve these beads and compress and recover the concentrated dye. And these dyes now can be reused by this batik treatment of the textile. So the advantage of our system is we can recover the concentrated dyes, whereas activated carbon, you cannot. You have to just incinerate the dyes. So this is something that we are very excited about, to try to take what we have to developing countries and try to demonstrate how this system can be utilized to remediate some of their water contamination problem. So we can envisage building a continuous system of columns that we can make the beads, and then once one is saturated, we can then switch off, regenerate, and then build this. So we can build a system that runs automatically by itself, and this is something that we are exploring in the future. So the next system was developed by one of my PhD students who has gone back to China. So she took CNF, which is a longer cellulose fiber, cross-link, activate with GTMAC, the silane coupling agent, and then cross-link with polyethylamine, and we got this particle that we extrude to nitrogen, liquid nitrogen, to then form these beads. So it's a very simple system: CNF, add GPDMS, and then cross-link, extrude. And then from there, we have the beads. We want to both remove copper ion, which is a nutrient and antimicrobial system, and then put it back into the farm for use. So this is closing the loop in agriculture. So you can see here, this is a demonstration of removing copper ions from this contender solution, and then the bead can then be transported or used in the agriculture field for both the treatment of the soil and also provide micronutrient. So now the bead is very, very dark. It's blue now because it's saturated with copper ion, and we can measure the kinetics at the same time. So the important thing is to test the mechanical properties. So these are about 2 millimeters. So we test them by using a tester that was developed in Waterloo. Very, very small and done in water. So we compress and release and to test whether our beads are strong enough. So you can see this without PEI, this with PEI is robust. You can release it, it comes back. So the beads are robust. It will not fracture or break. And this demonstrates that we have a system that can be used to remove nutrients, this is copper ion, and then reuse it in the field. Okay, the last system, last example I want to illustrate is regards to water, right? Water can be from ground, from the surface, or in the atmosphere. We found that there are 60% of fresh water in the air of Great Lakes. So the amount of fresh water in the air in terms of fog or clouds is about 60% of fresh water in the Great Lakes. So lots of water, right? In some places, like up in the mountains where there's no river and lakes, then this could be a very, very useful technology to try to develop. So let's see what we have done. Okay, so we did a review of this fog harvesting, dew harvesting, moisture harvesting, solar harvesting system, and that was published recently in Nature Water, demonstrating that this is a very, very interesting concept to try to learn from nature and try to innovate some of these physics into our system to do that. So we developed a very simple system I'm going to explain now and try to capture water from the atmosphere. So traditionally, what has been done is that they machine or make rough surfaces, micro nano structure surfaces, so that the surfaces is like lotus leaf is super hydrophobic. So we review this system, and then they then surface coat or modify the surface, and then they're able to demonstrate that this surface is able to also capture water. However, our system is very much sustainable, and we use all materials from nature. So we use plants, and from plants you get pollen. So now in Canada, it's springtime, lots of flowers, lots of pollen produced. These are very important resource. We have wax from many plants, and we have cellulose that I've just explained to you before. And then these are 3 different raw materials that is from nature. We can incorporate them and build a surface that is rough, there's micro nano structure, and that allows us to be able to prepare super hydrophobic surfaces that we can use to capture water. So let me explain how we do it, right? So essentially what we did was that we take wax, we heat up 60 degrees, it's become liquid, we put CNC in the water, and then we emulsify. Right, and we make these droplets, these wax droplets. They're about 3 to 30 micron in diameter. The more CNC you use, the smaller the particle, because there are more CNC at the surface. As you can see, the surface is quite rough. And we vary the amount of CNC from 1 milligram per mil to 10. So we are trying to imitate or to look at, in this case, a desert beetle, how they're able to capture water and harvest it and bring it to be consumed by themselves. So we take this wax and the CNC and we emulsify, make the wax droplet, and then we do a solvent exchange and spray coat it onto a substrate. So now the surface is super hydrophobic. We then subject humid air to the surface and monitor the water droplet capture. We measure the weight of this plate versus time. And when the water droplet becomes large enough, gravity will take it down. We measure another weight, total amount of water collected. So we try to look at the partitioning of the CNT to the interface, and if you suction and remove the water, we get this sparkling, demonstrating the surface now is saturated with CNC. And we can then do analysis, and we can look at the amount of CNC absorbed at the interface. And as more is absorbed, the particle size drop from 30 to 3 micron. So now we want to prepare with spray coated. You can control the height and the width, and that would control the roughness, and that allows us to be able to manipulate the super hydrophobic characteristic and also the adhesion property. So the trick to our technology is the super hydrophobicity in the macro domain, and then at the nano domain, we have hydrophilic CNC that would nucleate water because of the hydroxyl group. They will interact with water molecules by hydrogen bond. So this is an illustration. So this is a live picture. You can see this is the surface of our coated system. Water nucleates and become big. It would drop down by gravity, and the surface is refreshed continuously without energy. So it demonstrates that we have a system now that we prepared using natural material, scalable process to build this system. So this is the design. So we have our surface, we have a humidity sensor, we have a camera, and then we have humidifier. We subject humid air to the surface, collect the weight versus time, right? From 1 milligram per mil to 10. As you can see, when the amount of water collected, then it cycles, right? It drops off, increase, cycle. So this is the indication of detachment and reformation of the water droplet. And at the bottom, number 5 is the amount, total amount of water collected over a certain amount of time. So we compare our system with the conventional system. So in this case, 80% relative humidity, our material here has about 5 liters per meter square per hour. So every hour, if you have a meter square of your surface, you can collect 5 liters of water. That's about how much we consume daily. So what's the advantage? Our process is simple, with tunable nanohydrophilicity. We can have continuous water harvesting without loss of efficiency in a sustainable, low cost with commercial potential. So we published this in Chemie last year. So let me end my talk by introducing what I've been very, very committed to, which is sustainability, right? So we have a new journal that was we accepted manuscript in July last year, and we have our first issue in January 2024. Our goal is to be able to provide a platform for scientists working in this domain of sustainable resource management, converting waste to useful product, remediating waste that's found in our resource, water, air, and soil, and just looking at how we can make our Earth a better place. So today is Earth Day, right? So this month, our journal feature Earth Day. So the cover page will be focused on Earth Day. We have an interview with one of the main people in Earth Day running this program, and we are trying to work and partner with different agencies to promote sustainability and resource management so that the Earth will be preserved for the future generation. And this is our goal, and we want to invite you to publicize our journal and to submit your good work, and we want to be able to provide a good platform for the discussion of how we together can contribute to sustainable resource management. Thank you very much. These are our acknowledgement of our funding agency, and I'll be happy to answer any question that you may have.